We have a product of sine x and sine hyperbolic x, and we're asked to show that the fourth derivative is actually equal to minus 4 times sine x sine hyperbolic x. We're going to need to differentiate many times here. So let's first of all find dy by dx and use the product rule. But just differentiate it. I mean, you don't need to write down u and v every single time because we're going to be using the product rule many, many times here. So just go with it. Sine x differentiated, cos x multiplied by sine hyperbolic x not differentiated, then plus sine x cos x differentiating the second function. There we go. Right, now for the second derivative, we can't do anything with that. Okay, I've got to now use the product rule on each of these. So I'm going to get minus sine x sine hyperbolic x plus cos x cos x plus cos x cos x and then plus sine x sine hyperbolic x. These two cancel. We're left with 2 cos x cos x. Okay, we're halfway through. And you can kind of see where the 4 might be coming from. We've got a 2, we've got cos x, cos x. We're gonna differentiate again twice, and it's gonna go back to the original, but just with we're gonna suddenly get another minus 2 coming out. But let's keep going. So the third derivative is going to equal minus 2 sine x cos x plus 2 cos x sine hyperbolic x. And then the fourth derivative, minus 2 cos x cos x minus 2 sine x sine hyperbolic x. Oh, then there's going to become another minus. When I differentiate cos x, I'll get minus 2 sine x sine hyperbolic x plus 2 cos x cos x. Okay, these cancel. I get minus 4 sine x sine hyperbolic x, which is minus 4y. And we've got our result. Hence find the first 3 non-zero terms of the Maclaurin series for y, giving each coefficient in its simplest form. So here's our Maclaurin series. We're going to need to be finding the function, the derivative at 0. And we can do this pretty quickly, actually. So y evaluated at 0 is actually going to be 0, because sine 0 is 0. And then dy by dx evaluated at 0. You could write x equals 0 if you want, but I'm just doing shorthand here. Now remember, sine hyperbolic x is also 0 when x is 0. So this is 0 as well. The second derivative. Hey, that's not going to be 0 because it's going to be 2 times 1 times 1. It's going to be 2. Third derivative. Is back to being 0. And then the fourth derivative, because it's just a multiple of the original function was 0, it's going to be 0 as well. Okay, so that's good to know. So when I put it in, that's 0, that's 0. Actually, loads of them are 0. And we're going to write down that sine x sine hyperbolic x is going to equal x squared over 2 factorial. And then remember, it was f double dash 0 was 2. And then I'm going to get lots more zeros until I cycle back round and do it again. It's going to be like the 6th term next that's non-zero. So x to the 6 over 6 factorial. But now when I go back round and maybe I should write it out. So when I find the sixth derivative, I just need to times through by an extra -4. So I'm actually going to get -4 times 2 cos x cosh x. And that means that the sixth derivative evaluated at 0 is going to be -8 or -4 times 2. And then I'm going to cycle back round the next non-zero one. All the rest will be 0 because we saw that the function, the first derivative, the third derivative were all 0. It's just every 4, we're going to get x to the 10 over 10 factorial. And then the 10th derivative, I'm going to be timesing through by -4 again. So then I'm going to get 32 going on. And those are the first 3 non-zero terms. Just got to work them out. This gives x squared, and then it'd be -8 over 6 factorial. That actually becomes -1 over 90 times x to the 6. And then 32 over 10 factorial comes 1 over 113400 x to the 10. So just be really careful here. But that is our answer. Finally, we're asked to find an expression for the nth non-zero term of the Maclaurin series for y. So let's just look at each of these and where they originated. We had x squared over 2 factorial and we times by 2. I've already highlighted that. But let me take the next one a little bit steadier. We had x to the 6 over 6 factorial. We times by 2 and then we times by -4 as we went around the cycle. And then this one here, we had x to the 10 over 10 factorial times 2, and then we were timesing by -4 again, so it became -4 squared. So for our nth term, well, we've got a little sequence here, 2, 6, 10, and so on. It's an arithmetic sequence, sorry. So you could either use your little formula like un equals a plus n minus 1d, or we could just use the ideas that we have from GCSE. We're going up in 4s. So it's going to be 4n. And then I normally say, like, go back to the 0th term, and whatever that is, you add on, we're going to get 4n minus 2. Or you might write down 4, 8, 12, and think, what do I need to do to get back to 2, 6, and 10? 4n minus 2. So our nth term is going to be x to the 4n minus 2. You can see it works when n is 1, when n is 2. This is a nice way to just sort of check it. And then we're dividing by that factorial, so 4n minus 2 factorial. We are timesing by 2. And then we are timesing through by -4. And it's actually, for the first term, we don't times through by -4 at all. But the second term, we times through by once. So I think it's going to become n minus 1. Yeah, so when n is 1, it's going to work out. When n is 2, it's going to work out. This is going to be our answer. We might just slightly tidy it up, just so I got the coefficients all together. So it's going to be 2 times -4 to the n minus 1 all over 4n minus 2 factorial multiplied by x to the 4n minus 2. Wow. Just to finish, I don't know about you, but I was wondering what this function actually looks like. Here it is, sine x times sine hyperbolic x. I had to put brackets around the sine x because otherwise it didn't like it and it thought I was actually finding sine of x times sine hyperbolic x. And let's see what happens when we start taking some of the terms. So remember, our first term was just x squared. Okay, it's looking good for small values of x, as you would expect, because the other terms are just going to get smaller and smaller. then I'm going to be minusing 1 over 90x to the 6, and suddenly, wow, you get that shape on the way down. Okay, but of course it doesn't work either side. And then we're adding 1 over, and this was quite a big number, 113400 x to the 10. Hey, okay, you get that bit there. Not amazing, but still pretty good from 3 terms to kind of function, the shape that we get. So yeah, it's really like that. New little function to consider. Well done.